Hello. Yeah, so today we are going to see what is expected value or expectation of a random variable. So this concept is generally used in a lot of disciplines of mathematics, science, statistics, and it is currently being used a lot, and it's a very foundation and a basic concept used in different uh, machine learning and artificial intelligence algorithms too. So we'll see what actually do we mean by expected value or expectation of a random variable, and what do we actually get from this expression as to whenever we write e, or that is known as expectation of something under this x being sampled from p of x. That is what actually are these terms, and we're going to see that. So as discussed, this is being used in many fields of maths and science. And before coming to this formal definition of expectation and expected value, let's get some intuition. So this is actually something like what we can estimate, or what can we possibly guess about a particular random variable. What is random variable? So let's take an example. So imagine that there is a person here, and that person goes to the banker, and the banker has five different boxes with some money in it, with some amount in it, and this capital M is the money that is being assigned to this person by the banker. So what does the banker do? Banker is a fair one. He just randomly selects any of these boxes, and whatever box that has been selected, the that particular amount is assigned to this capital M, and this is the money that the person takes. And this experiment or this event happens like periodically, you can say maybe on a monthly basis or a daily basis or a weekly basis, but this keeps on happening again and again, again and again and again and again. So what do you think if someone asks you that at any instance, if this experiment is conducted in the long run, or very very large number of times, what do you think this at any instance this M could be? So to formalize this, let's consider the possible values of this capital M being M1, small m1, m2, m3, m4, and m5. So M can possibly take any of these values and not any other values apart from this. So we can say that we only have a finite set of amounts that this person can possess at any instance. I'm not talking about that this is going to be accumulated. It is just like once it will be having five. At another instance, when it will be this person is going to the banker might give this person a 4, or randomly a 2, or whatever box that has been picked up. So a very simple and naive way to get the estimate of this M at any instance, if this experiment is performed in the long run, is just to sum these up and get the average. And in our case, it will be just 5 plus 4 plus 3 plus 2 plus 6 divided by the total number that is there, 5. And this is a very naive way of saying that, okay, what is actually the possible value of M at any instance. So this is generally the average in the long run, and this long run is a very important statement. Now let's change the setting a bit, and let's have 4 of such boxes. So now we have 4 boxes of 5, and rest being just 1 boxes of 4, 3, 2, and 6, over total of M1 to M8. So now my possible values for this capital M are M1 to M8. They are still finite. And if someone asks what is the estimate at any instance, we are not going to do anything apart from just taking the average of all the possible values that could be possibly assigned to M. And this is, if you can see 4.375, and we can see that this is actually tending towards 5. I mean, we are having 4 of these, and let's imagine if I have thousands of such boxes, and almost 900 boxes are just containing 5. So you can intuitively think that this will be this particular value will be very, very, very much closer to 5. And another way of writing this particular summation is 5 times 4 plus 4 times 1 plus 3 times 1 plus 2 times 1 and 6 times 1, and that can possibly be reduced to this particular expression. So these are the actual values that are going to be assigned, and this is like how likely, why we were saying that it is tending towards 5, because 5 was more likely to be picked by the banker, because more number of boxes were there that had 5 in it. So we can say that 5 was more likely to be picked by the banker. And so this is just the probability of these amounts being assigned to this capital M. And why we are saying it probability, because if we say that an event that is happening has a probability P, it simply means that if that event or experiment is conducted, or that experiment is conducted infinite number of times, or for a very, very long time, or for very large number of times, then the proportion of a particular event being that particular event would be T times the total number that has the total number of experiments that have been conducted. So this is what we mean by if an event is having a probability P. So now if we can reduce this to some symbols, this is actually just m1 times the probability or likelihood of m1 being there, then m2 times probability of m2 being there, and so on and so forth. And this can simply be the sum of whatever possible value that can be assigned times the probability of that value being assigned to that variable. And this capital M is the random variable, because randomly it can hold any value. You don't know which value is going to be assigned. It totally depends upon how likely that value is going to be assigned, but it is still going to be random. And this is why this is known as a random variable, because the values keep on changing. And how is it changing? It is changing randomly. So we can define, and this expression is nothing but the expectation of this random variable, where the possible values are governed by this probability of those individual values that could be possibly assigned. So we can say that expectation of something is nothing but summation of something times the probability of something. As simple as that. Expectation of something is the summation of the product of something times the probability of that something to occur. Now if we change some settings again and change the game and see that whatever value that was being assigned by the banker, let's say that was MI, this person actually went to a machine, and this machine actually just did a square of that value. So let's say if 2 was assigned, we would be getting 2 square, that is equal to 4. Now this particular machine is dependent on MI, right? So whatever the value of MI is, this machine is going to output the value accordingly. So I can say that this machine is some function of MI, and because this is small mi, I can say that there is some small yi that this machine can, these are the possible outputs of these machines, m1 square, m2 square, m3 square, m4 square, m5 square. So whatever possible values, I'll just square them up, and those will be the possible outputs from the machine. Now, if we in the first setting, what do you think would be the possible average output values from the machine? So we can simply do the same thing. These were the possible outputs. We can take the average and get some value, and this would be estimate for y. And in the second setting, in which we had 4 of such boxes that had 5, again that could be reduced to this particular expression divided by 8, and then I can simply again write the same thing, because 5 was occurring 4 times. I can say that it is 4 by 8, and then 1 by 8, 1 by 8, 1 by 8, 1 by 8, and these are the possible outcomes from the machine. What are these possible outcomes? These are nothing but f of m1, f of m2, m3, m4, m5. And what are these? These are nothing but the probability of m1 being assigned to capital M, m4 being assigned to capital M, and so on and so forth. So this can again be reduced to a summation of f of mi times the product times the probability of small mi. And this again is the expectation of f of m. So again, as we said, expectation of something, and in our case this something is f of m, where we are sampling the values of m from this, or these possible values of m are actually following this this probability, and this is the expectation of f of m. What do we actually, let's get some insight as to what do we mean by every time when we say a distribution or probability distribution. So in our second setting, we had 1 2 1 3 1 4 4 of 5s and 1 6. So this is how these amounts were actually distributed in the bank. These many number of 5s were there, these many number of 6s were there, these many number of 1s were there, 3s were there, and 4s were there. So whatever possible values that a random variable can take, the way that we distribute those values in is known as the distribution of those m's, and this is nothing, and if so we are just maintaining the count, and if we just convert that into a probability, we are just having the distribution like 1 by 8, 1 by 8, 1 by 8, 4 by 8, that is 1 by 2, and again 1 by 8. So this is known as the probability distribution of m's, how they are distributed wherever they are in that probability space. And intuitively this could be anything, this distribution could be anything. So this actually for discrete, because these are finite values, these are discrete values that are possibly being assigned to m. So this is known as the probability mass function, and we have these two properties, as in these probabilities will always be in the range of 0 to 1, and if we just sum them all, it will be equal to 1. Same thing we can say for continuous variables, as in let's say that this m can take any real number, like any real number, like this, anything could be possibly assigned. But how these real numbers are distributed, again let's say in the bank, would be given by this. So this is the distribution of these numbers, and if we go and we select any number here, that is xi, this particular point is the likelihood of xi. And likelihood is a bit different terminology from probability, and if we consider this continuous probability distribution, so this is generally defined for a very small region. So we define probability for, let's say, this dx. So if we want to say that what is the probability of lying within this small region? That would be p of x times dx. And this is known actually as the probability density function. It is more than 0, but it could be more than 1 2. And if we just sum them all, we will be getting it as 1. So the area under this curve is always equal to 1. And for extending this formula for continuous case, as we said, expectation of x coming from a distribution would be summation times something multiplied by the probability of something, and that could be given by, in continuous term, that summation actually becomes this integral of something, that is the x, and this is going to be the probability, and this is the expectation of x in continuous domain where x is coming from a distribution p of x. So now if we see the formal definition, that the expectation or expected value of some function f of x, this is something with respect to a probability distribution p of x, is the average or mean value that f takes when x is drawn from p. So we are sampling x from this p, putting in here, and we are getting this expected value. And same thing for continuous random variables. I hope you got the idea of what actually expectation of a random variable is. So we got to know that expectation is given by this definition. A random variable, what is random variable? This is what we got to know, and a very naive understanding of what do we mean by a probability distribution.